My PhD topic is about sports motion analysis, especially from competition videos to data-driven interpretations. So for coaches, they study the athletes' performance, not only by their expertise, but also use some biomechanical features to help them with their analysis. And the good thing is that World Athletics, the organization, publish biomechanical research reports so that they provide some ground truth for the coaches assisted with their study. However, the bad thing is that they only publish very few data, so it's not sufficient for the coaches. And if the coaches wants to measure the biomechanics by themselves, it's time consuming. A good thing is that there are many videos on YouTube, online, and many other resources. So the problem comes, how can we use the online videos to help coaches? Despite there are many these kind of videos, we have the first problem is that these videos are not ready-use data. So we have limited athletic post data, especially for the online competitions. The videos are monocular, which is shot by single camera, and the dynamic by moving camera as well. So the first thing we do is that we constructed the two long jump data sets and made them open and perform the analysis based on that. When we have the data set of the images, especially, it's not ready to use for analysis. So people use human pose estimation. Here is HPE to get the skeleton joints of the athletes so they can perform some measurements. This problem has been widely studied and people get very good perform the models. However, because of the videos of online competition is different from those people used to train models, there are huge domain shifts. From this example, we can see that the bounding box doesn't do very well for detecting humans, and the key joints also has huge errors. So to address this problem, we proposed a model that can do pose finding, especially for 2D poses with the prior knowledge. And with the pose sequences, people can calculate or measure the biomechanical features, and that can be used by the coaches. However, currently there are scarce data of those kind of features, and how to obtain them is still under studied. So after previous one, we proposed a data-free feature estimator that we want to facilitate with this problem. Then it comes how to analyze this data to facilitate coaches with the help coach to analyze the performance of the athletes. So currently, coaches usually use physics or statistics but these are difficult to model some nonlinear complex relationship between the features and the performance. So we first formulate this problem here. We want to use machine learning and deep learning to model those nonlinear relationships. There are two modalities we can choose. The first is pose sequence, and the second is biomechanical features. Besides that, we also have performance related to the movements of the athlete. Here for long jump, it's distance. And with the models of AI, we can train some predictor that can model a relationship between input and the performance. And so the objective will be to find the important feature or patterns in the input feature through the trained model. It naturally brings us to explainable AI, and that's what explainable AI supposed to do. So for the analysis, we did another three contributions. The first is that we analyzed the biomechanical features from the constructed data set and with explainable AI methods. And in this work, we find that the interaction between features become a big problem if we use the these explainable AI methods. So we further proposed a new feature interaction visualization method to help us with this kind of analysis. So in this way, we studied the biomechanical feature modality. Another path is that we would like to find some important patterns from the human post sequences. That's not, in that case, we don't need to rely on expert knowledge for biomechanical features. So here in this work, we proposed a new multivariate time series black box explaining model, and we find some meaningful patterns for extracting some important features. And when we look back into the formulation, actually, this work can have broader impacts if we're analyzing human motions relative to another metric, for example, injury or other sports. Now we are going to introduce the details of those work we have done. First, we have the overview at the top. So we will start with introduction of the long jump and then describe briefly the constructed data set. And then we have 4 main contribution parts, including the 5 very important ideas we studied previously. First, for the long jump, from the athlete and the coach perspective, it can be divided into 4 phases. In approach phase, the athlete run as fast as possible. And in the takeoff phase, they convert the horizontal momentum into vertical one. And in flight phase, they follow a projectile trajectory. And finally, they landed in the sandpit. To study this process, people has proposed many biomechanical features, which can be step lengths or velocities. We can see here in the bottom figure that the distance can be decomposed into several parts, where the largest part is decided by the velocity, and also the inclination angle of body trunk, and also the knee angles and the side rotations, etc. So we are going to the second part, which is about the first idea that we proposed to address the human pose estimation problem. Sorry. We go to the details about the constructed data set. Before this, we did a little literature review on the data set used in long jump. So we can see in the right figure that most of the data sets are below 30 samples. So in this community, data sample is a very big issue. And to address this, we constructed 2 data sets. The first is world champion long jump, which consists of biomechanical features taken from the reports of the World Athletics. And also, correspondingly, we have the labeled videos. In this data set, it will facilitate us to study biomechanical features and also the human pose estimation parts problem. The second data set is elite long jumps. For this one, we would like to focus more on pose sequence and train a slightly larger model to our best. So we collected 386 samples of jumps, and each has 50 frames of pose sequences. In these 2 data sets, as I mentioned, the previous one has been used in section in the main contribution part 2 and 3, and the pose sequence of the first data set is used for human pose estimation, while the second data set will be used in the pose sequence analysis in part 4. So now we really comes to the ideas we proposed. We would like to study, as we mentioned previously, the human pose estimation of the state of the art doesn't perform that well on competition videos. So people have studied this problem mainly follow two approaches. The first approach is that they fine-tuning the pose estimator. This relies on image level, this works on the image, so the image level diversity, like a light, background, camera view, will influence the performance, will influence the performance, and there will also be domain shifts as we addressed. So to address all these problems, we need a large data set, still slightly large. And the second approach is to directly post-processing the skeleton sequences. So in this case, we don't need the image, but only focus on the poses. Potentially, this method will be more data efficient. People study this right now are mainly through temporal continuity, which the good thing is data-free, but it's kind of restricted to other applications. So what we think is that, can we tell if pose is good or not, like human beings using the prior knowledge about poses? We followed this work which studied the 3D pose prior using neural distance fields. So they assume that all the plausible human poses lie on a high dimensional manifold, which is 0 level, which means that the real pose has distance of 0 to the manifold, while the fake or bad pose, they are outside the manifold, so they have a positive distance to that manifold. In this case, the distance of become fields, which we call it distance fields or neural distance fields. And the advantage of this method is that with these distance fields, we can calculate gradient easily, and so that we can project the fake pose by gradient to the manifold to become a good pose. They model these fields with a neural network. And to train this neural network, we need some data. So we have real poses already, and we know that the distance of the real pose is 0 to the manifold. So we have these samples ready. For fake poses, people generate a fake pose from real pose by adding some noises. And to calculate the distance of the fake pose to the real pose, they find the nearest real pose to that fake pose, and using a distance function to calculate the distance so that it construct fake poses. In this way, we have the training data to train the model, and we can learn the manifolds. It works well on 3D real-world poses, but if we want to apply it to sports poses, it will be difficult because 3D sports poses are different from daily poses, and it's difficult to obtain and limited in availability. So what we want to apply is that we want to use the pose from abandoned videos. So we studied 2D pose priors so that we have more data for training sports poses. However, 2D pose prior is more challenging because one 3D pose can be projected to many 2D poses, actually infinite ones. So this comes the main obstacle of this approach is that we need to address the data efficient problem. The main contribution in this work is that we proposed a polar coordinate representation and the data augmentation methods to facilitate the training of this 2D pose prior. The polar coordinate representation is shown in the left figure. So it's actually very simple. We focus on joints, and we focus on the angle between the connections and also the length. The good thing is that we separate these two so that we can put more stress on the angles without losing positional information. In that case, we are more robust to camera rotation. And the second point is that when we generate noisy poses, we don't fully rely on random noises because we want to be more data efficient. So we sample the errors of those 2D human pose detectors plus some random noise. So that makes the fake pose more targeted on what we want to do. And the third point here is that when we train the model with bad fake samples, which is outside the manifold, we don't only use it for training. When we train it on these samples, we also perform gradient projection so that we make a correction with our current version of fields, and we recalculate the real distance, and we then further training our model with the new generated data sets. So with this data augmentation method, we can use the data in a more efficient way. Then this table shows the main results. We tried 3 different human pose estimator, alpha pose, HRNet, and VIT pose. The first row for each estimator, we didn't use any refinement, so they are raw output of these models. And the second row, we refined with 100 iterations with our trained pose prior. What we see is that we get quite good, we get improvements for every case, but the problem is the improvement is limited. It's not a very huge improvement. So we further studied why this happens. Actually, during the iteration of the correction, the distance of the poses or the accuracy of the poses can change differently. We see the below example. For sample 1, along the iterations, the accuracy get increased by steadily, but for sample 2 and sample 3, it may be corrected at certain iterations, and after that, it's getting further and further from the manifold, and the accuracy drops. So when we only record the performance at 100 iterations, it may not be the best performance ever achieved. So what we do is that we check the best performance achieved during the iteration per sample and aggregate them. What we see is that the performance gets much better than what we have. So this indicates that we have some convergence issue when we do the correction. That's also a problem of current methods. Further, we checked the joint-wise correction. So we have here 19 joints. We check how each joint get corrected across the iterations. We see that for most of the joints, first we look at the left figure, which is about PCK at 0.05. This means a final grade accuracy. So from this level, the performance are already, most of the performance are not as that good, but actually this is because 0.05 means 5% of the connection length, so it's very strict criteria. And we see that there are some joints that the accuracy increased. So those are right shoulder, right elbow, and the nose. And when we look at the right figure, it's a more coarse accuracy because it's at 10% of the connections. So we see that head and the nose also get increased. But because this model, we use the alpha pose, which already predict good poses. So most of the joints don't improve that much. Is a very understandable thing. And those increased a lot actually are about the right arm. This is because those arms are frequently occluded, as we see from the right figure. So they predict badly by those pose estimator, but in our case, we improved them. And also the nodes, because the definition of nodes of different methods have some domain shifts. So we also improved this quite good. And the second main contribution is about biomechanics. So we want to get biomechanical features from input frames. The key step is to get the global trajectory. When this work was done, little research has addressed this problem, but in recent years, many deep learning models has proposed to estimate the global trajectory. But compared to them, our methods still have some advantage. It is that we are data frame, so it makes us more data efficient. Actually, the idea is very simple. We consider the running of most of sports, which is a very important process. During running, there are two phases. The phase one is that we have 1 foot on the ground, so the foot will be stick to ground. In this phase, if we have the 3D poses, we only need to fix their joint up at the foot which contact the ground. So we get the pose at their global position. And furthermore, we can calculate the center of mass during this phase, and then followed by phase 2, that the athlete is fully in the air, and the center of mass will follows a projectile trajectory. And when we have the velocity of previous phase, then we can easily calculate the following trajectory, and then we reconstructed the whole trajectory, which we show in this slide. The middle row is the side view. We see that the side view of the long jump trajectory is estimated quite good, but from the top view, which is upside, we see that there is slightly curve. This is because when we use the competition videos, the camera rotates to follow the athlete, and then we see the perspective of the camera to athlete is changing. Furthermore, we use those trajectory to calculate the biomechanical features. The results is shown in this slide. In this table, we see the first column of figures, which we use ground truth annotation of the foot touching the ground. The accuracy is not very good. Then we checked what happened. So we realized that the frame rate of the competition video is 225 frames per second. It is kind of low. So we check the neighbor poses and calculate these features to record the best one, and we get much improvements. This infers that our model performance is highly restricted by the frame rate. Especially we look at the takeoff leading side, which didn't improve. During takeoff phase, the mean angular velocity for this is 558 degrees per second. So with 1 frame change, it's already 23 degrees. So this will cause us problem when predicting those highly faster changing features. And the next, we would like to address how we can interpret the biomechanical features. As we addressed previously, experts currently study this with physics or statistics, which is some statistical regression, which is not sufficient to describe the nonlinear complexity relationship between feature and the athlete performance. So first, we propose to use a quantile regression forest. Here we use quantile regression method, which is different from normal regression. Normal regression assumes the distribution of the target is normal distribution, but for our case, we put our focus on the specific quantile using the pinball loss. So we set the quantile to be 90, which means we want to focus the performance higher than 90% of all the performances. And with this, we model the relationship between feature and the performance. Then to explain this model, we rely on sharp analysis, which is described by this equation. On the right side, we see that the effect, this part shows the effect with the feature and without the feature for certain sample. And on the left side is the weighted sum of all the combination of the feature set. So it will give us the attribution or the importance of each feature for each sample. And then we also use partial dependence plot to check how one feature or two features influence the performance numerically. This slide shows the sharp analysis results. We look at the top side results. We can see that the velocities are the most important feature, especially the last step, horizontal velocity, which is same as the common sense. The second is that we find the touchdown knee angle is also a very important feature, which ranks at the second, which is less addressed in literatures. And we also looked at instance level performance of the analysis. We focused on the best performance, and we see that still last step horizontal velocity is the best, is the most important feature, and the touchdown knee angle follows the other velocities. And to look at how these features actually influence the performance, we check the 2D partial dependence plot. And here, for each plot, the horizontal is corresponding to one feature, the vertical axis corresponding to another, and the color represents the performance. And the contour has been also drawn in these two plots. A very obvious phenomenon is that we see there is some step change at a certain value of the touchdown knee angle. For the left is the horizontally, we see there is a gap, and for the second we see vertically there is a line split these two parts. This corresponds to 169 degrees. This has been partially addressed by CFAS, which explains this phenomena that the takeoff distance decreases as the touchdown angle, knee angle decreases. But here the good thing is that we also see how this influenced the final performance numerically. Another phenomenon we observe is that there is interaction between knee angle and the takeoff velocity. For example, if we look at the right side, both axes have influence together to the performance. So this is not very good thing, because sharp analysis assume that the feature contributions are individual and additively. So we would like to further study how this interaction happens. However, there are few works study this problem, especially to show how numerically the interaction happens. We take one of the most famous method DIs here as an example. We set up a toy example, which is a random variate from dependent on three variables, and the two of them has interaction. From the DI's plot, the left side is for x1. It's totally random, means no interactions. For the middle one, it seems there are two modality, but still it's hard to tell interactions. For the third one, we see that at the value of 0 for x3, which corresponding to the step function of x3, there is huge interaction, which is quite different from the others, but we cannot have further information like how this interaction is and with which features the interaction is. So we further propose a visualization method to analyze this interaction. First, we would like to define the notations. We study the predictive model from X to Y, and we have one feature of interest, which is XS, and for the rest is XS bar. And the interaction here also is different from common understanding of relationship between features. It is stick to a performance or a predictor. So actually it means that if the two features collaboratively influence a predictor, the prediction of the model, then they are considered interacts with each other. Then start with this notation, we can do some analysis. First, we write the predictive model as the addition, as the sum of a constant value, and the Fs is the one only rely on the feature of interest, and the Fs bar is the part not relevant to the feature of interest, and lastly is the interaction parts. So here we assume that these interaction parts can be decomposed into the sum of in this form, which has been applied also in other methods. Then we get the second row, we write it in a decomposed fashion, and then we take a derivative over xs, which is feature of interest. We can get this expression. Then we further take the expectation over the feature not of interest. So we find the expectation of xs derivative with respect to xs. It can be expressed very simply in the right way. With these foundations, we can find the way to calculate interaction terms. We go to the first row, we have the interaction expression. So if we take the derivative, is equivalent to take the derivative of the rectangular parts in the second equation. And this one can actually, using the later two expressions, we can write it in the final expression here. It's easy to calculate because the first part in the last equation right side is actually the ice function, which is already been well documented in current software and studies. And the second part is actually the partial dependence function, which is also very easy to numerically calculate. So then we go back to the previous toy problem with our method. First, we check how the interaction happens. The interaction term, it can be right in two functions, one relatively to x3, which is a step function, and the other relatively to x2, which is a linear function. And in our case, we recovered how these interactions. For the left figure, we see that there is a step change along the value of x3, but no obvious tendency for when we along the vertical axis, which is x1. For x2, for the second plot, we see some tendency, then which is better visualized in figure at the right side, which shows a linear relationship with the x2. And then we apply this to a real world model, which is bike sharing. Something interesting is that we find there is interaction between temperature and the hour. So the interaction term for temperature is a linear is kind of a linear function, and for the our parameter, which is we can say it's two peaks, which we assume that we infer that is corresponding to the time people go to work and go off work. Finally, we also apply this method to our sports data. But we can see that the data set are really small, so it's very scarcely hard to draw some strong conclusions, but still we see there is some tendency. For example, for the left figure, we see at the left side, the values tend to be higher, and at the right side, the value tend to be lower. But yeah, and for the right side, we also see some tendency, but still we need a larger data set to facilitate this kind of analysis. And lastly, we would like to study how we can find the motion patterns from the post sequences. The objective is to extract influential movement patterns, which can be considered as spatial temporal patterns if we consider the whole sequence as a multivariate time series. So not yet exists. There is not yet work study sports post sequence interpretation yet. So in this work, I collaborated with Khalid, and we proposed a time series sparse autoencoder, which can generate counterfactual explanations. The counterfactual means the targets to find the minimal inputs that can change the model's output. So by this way, we can identify those most important parts in the input that influence the model output. The model is briefly described in this schematic. So we have the time series input here, and we have the black box model to generate a prediction. And what we do is that we train a sparse autoencoder here, which generates concepts in the middle that can reconstruct the input time series, and we refeed it to the black box model to generate another prediction of Y. We do this in this loss term, so that first we check the reconstruction X if it's well reconstructed. So we use this loss term, and the second we want to add some further supervision. So we checked if this prediction are consistent. By these two loss term, we make the model works. And to further improve the performance of this model, we consider the faithfulness and the outer distribution. So for faithfulness, which is on the right side above the equation, we use positive pairs and negative pairs in the contrastive loss, which we want to ensure is that those closed samples, when we add some, when we change the concepts here, with the same intervention, we check the closed input sequences. For those inputs that are close, our intervention should generate a similar output. But for those negative pairs that we use different interventions, it should generate different outputs from the positive pair. So by this way, we ensure the faithfulness of this model, and we also consider the outer distribution scenario. So we consider the reconstructed data as a new sample to perform a kind of data augmentation and refeed it back to the encoder to ensure that the embedded concepts are same. So in this way, we address the auto distribution problem. And finally, we applied it to the long jump. So here I show example of two different jumps. Jump one is a good performed jump, and jump two is the one that performed much worse. The activation concepts we extracted from the model is shown in below. The left side is the good jump, and the right side is the bad jump. So what we see is that there are certain concepts highlighted in the feature map. If we look at the good jump activation concepts, we see that this row corresponding to the knee key point is highly highlighted, and this row corresponding to ankle are also highlighted, and they are activated in the rhythm of steps. So this is corresponding to what we obtained from the biomechanical feature analysis, that the last step, horizontal velocity, is very important. Here we see that the steps is kind of this rhythm kind of related to the velocity. And also the second is the touchdown knee angle, which we also identified it as important in the activation map. So finally, it's conclusions and perspectives. In the human pose estimation part, we developed a method to using 2D pose prior to refine the pose estimations. So our method performed well, but still we find the poor convergence issue when we correct with a lot of iterations. This problem has been unsolved and resolved. So there are two possible solutions to address this. The first is that we may need to find a better distance definition, because currently our distance definition will influence the format, the manifold distance field. So a better definition of distance may reflect the more truthful the distance really is for 2D poses. In that case, it may help us with the corrections. And another is that extra supervision might be also helpful, for example, using temporal continuity. We tried this, but currently we find our data set just the frame rate is too low, so the pose sequence is not that much continuous itself. So it's maybe with a better data set we can address this issue. The second is that we constructed a 3D trajectory and estimated the biomechanical features, but we see that currently our data still face the problem of low frame rate. So that should be addressed in the future, for example, using models to interpolate those high-speed human motions. And for the interpretation with biomechanical features, data size is an issue for us to draw really strong and robust conclusions. And for our feature analysis, feature interaction analysis method, we didn't yet compare with other method, because most of the other method propose a metric to evaluate how strong the interaction is. So we may need to develop a metric from this method, which is ongoing, and then we can compare with other methods. Finally, for the human pose sequence, our method gets some interesting conclusions, but it's only instance level explanations. We would like to further this work to study the global level explanations so we can get more robust conclusions. And lastly is some future work that outside of this this project the work we have done right now. First is the physics plausibility in human pose estimation. This is a very interesting part because actually the main constraint is the physics, but it's well studied. It's studied in many works, but still not well addressed in deep learning models. They mainly use some physics engine to assist with the estimation. And the second is generative AI for sports motion and the data set. We see from some news that currently generative AI generates very good videos, but when it comes to sports motion related ones, it's still not very good. In this way, maybe we can also facilitate with construct some data set for other purposes. Lastly is that in the biomechanical feature analysis, it's better to incorporate some causal explanations. But for our case, we just have too few data to do this. Finally, is the publication list, which included some work published in conferences and some still working on the review and some not included in proceedings. Thank you very much.